A loop of thread is lying on a smooth horizontal surface. Our interest is to find the tension in the loop as it rotates. The radius of the loop is r, and mass per unit length of the rope is mu, and the tangential speed of any element of the loop is v. Now, if you consider the loop as a whole, the tension is an internal force. If it's lying on a smooth surface, the forces would be the normal reaction and weight, which balance each other. Each element of the rope exerts a force on the floor, and normal reaction force balances that weight of that element. And this is true for all elements of the loop. Now, our interest is to find the tension. Tension is an internal force, and Newton's second law demands that F be external to involve it in the equation. So we have to consider a part of the loop. Now, if you consider a large part of the loop, then different elements of that loop have different accelerations towards center. Each element has an acceleration of v squared by r towards the center. So if you consider a large portion of the loop, you will have different directions for the accelerations of different elements. So we pick an element which is so small that we can say the acceleration of that element is towards center. So this is that element, tiny element, and I've zoomed it up a lot. And these are the forces exerted by the neighbors of the element, T and T. Now let this element subtend an angle of d theta at the center of the circle. This is a very tiny element. This subtends an angle of, say, d theta at the center. We'll draw the symmetry line which also goes to the center, the bisector of this angle. So this angle is d theta. Then if I draw a tangent here to the midpoint, this angle will be d theta by 2, d theta by 2. So you can split the components of the tensions towards the center and along the tangent. Along the tangents they balance out, t cos d theta by 2 and t cos d theta by 2 balance out. Towards center, t sin d theta by 2 and t sin d theta by 2. That is 2t sin d theta by 2. That will be equal to mass times acceleration of this element. The element subtends an angle of d theta at the center of the circle, then r d theta is its length, and if mu is the mass per unit length into length of the element. That is the mass of the element, dm, into acceleration, v squared by r. Well, we picked an element because we know the direction of its acceleration. If you look at more than one tiny element, then accelerations are in different directions. So in the second law of Newton, if you know acceleration, you can find the forces. So that's what we are doing. We know the acceleration from the behavior. In circular motion, the elements have acceleration of v squared by r towards center. So we know the acceleration. And then sin d theta by 2. D theta is a very small angle. So this would be d theta by 2. Sin d theta by 2 will be d theta by 2. And there is 2 here, so this becomes t d theta. That is mu r d theta. This r goes away. This r goes away. So this is mu d theta v squared, and this d theta goes away, so t equals mu v squared. That's it. That's the tension in the loop. We rarely pick an element of any object to write the dynamics equation. Dynamics equations are mostly for the entire object, m, not dm elements, because all the dm's of an object which we mostly study have the same acceleration. Here, different elements of this loop have different accelerations, and you cannot consider the whole of the body because then tension will be an internal force. So that's what we have done here. There is another interesting way of solving this problem. We'll consider a semicircular portion. Why a semicircular portion? You can consider, well, 1/4, the quadrant of this, but semicircular portion is very convenient, as you will see. The force exerted by the other half of the loop on this are T and T. So these T's are parallel now. And different elements of this semicircular portion have different accelerations, but Newton gives us a way of dealing with these systems. Find the acceleration of the center of mass. That's interesting, right? Even if different elements of a body have different accelerations, we can write an equation for that behavior if you know where the center of mass is and its acceleration. Now, where is center of mass? Say at a distance of small r from the center on the symmetry line. That small r is 2 capital R by pi. And what is it doing? It is rotating along with the semicircular portion with the same angular velocity. The linear speed, of course, would be different because this is a larger distance, capital R, and this is small r. So this center of mass, which is 2r by pi from the center of the semicircle, has an acceleration of r omega squared. We'll switch to omega because v of this and v of this are different, but omegas are same. So that will be r omega squared towards the center. The resultant force towards center is 2t, right? The t and t are parallel here. That will be equal to mass of this, mu into pi r. Pi r is the length of the semicircular portion, so mu is the mass per unit length. Into acceleration. Acceleration is what? Small r omega squared. Now we are using omega because omega for the center of mass is same as omega for the semicircular portion. Well, the v value would be different. So we can find that v2. V will be in the ratio of distances, right? V is capital R omega here and V of this is small r omega. We don't want to do that, so this is simpler. So this is mu into pi r into r. This is 2r by pi into omega squared. So pi goes away. This 2 goes away with this. So this t on this side is, this is mu. This 2 is got cancelled here. This is r squared omega squared, r into r squared omega squared, and well, this is mu v squared. Pretty elegant way of solving, right? So this is a very nice application of that dynamics equation written for a system of particles where accelerations are different for different particles. If the particles all have some order there, we can know where the center of mass is, and if we know the acceleration of center of mass, we can involve that in a dynamics equation. Thank Newton for this.